Okay, so I recall that a point of this space is an n-tuple of integers. And I defined for every n a Markov semigroup on this space. The problem is how to define some limit of this semigroup. So the problem is what kind of limit I mean. I will explain this. The first claim I need is the following. I will state it first, and next I will explain its meaning. The claim is as follows. A projective limit of simplices is a simplex 2. What does this mean? What is a simplex? This is a well-known object. If you want to define a geometric simplex, this is a geometric body in this is the dimension. So this the same is dimension, and you have m plus 1 points and a convex envelope of them. So in one dimension this is a segment, in two dimension triangle, tetrahedron, and so on. What is a map of one simplex into another simplex? Okay. The key observation is that any point of a simplex is a convex combination of its vertices, and in such a way it can be represented uniquely. So one can say that any point is a barycenter of some probability measure supported on the set of vertices. So the idea is as follows. A simplex is just the set of probability measures on a finite set X. In this situation, if the dimension is m, the number of points here is m plus 1. But we can go further and define a simplex in the case when X is a discrete countable set. And even more, we can define a generalized simplex, I will say simply simplex, in case X is a measurable space. So it is a space equipped with a distinguished sigma algebra of sets. Now, what is a map? One can say a fine map of simplexes. This is a map from one simplex to another simplex, which preserves the operation of taking barycenters. So to define such a map, it's enough to indicate what are the images of the vertices in the discrete case. Once this is done, the map, the affine map, is defined uniquely. But if you identify a simplex with the set of probability measures, where X is the set of vertices here, and say, we see that in the discrete case, an affine map is the same as a stochastic matrix. So affine map is the same as a Markov kernel, one can say. Markov kernel. I will define it as follows. From X to Y. Meaning, in the discrete case, this is just a stochastic matrix. And now, the meaning of these this claim is as follows. Assume we are given a chain of spaces, say x1, x2, and so on, and the dash arrows represent some Markov kernels. So this is some Markov kernels. Here is, and in general, my notation will be x sub n to x sub n minus 1, and the Markov kernel will be defined with upper index n and the lower index n minus 1. Okay? And such a sequence induces a sequence of affine maps. These are not maps. These are Markov kernels. But here we get ordinary maps. And so on. So I want to take the set theoretic projective limit of this sequence of ordinary maps. So I can form projective limit of these spaces. What is an element of such a projective limit? One can term it a coherent sequence of measures. So an element of a projective limit, element of this projective limit is a sequence of probability measures on the corresponding sets such that they are compatible with the links, meaning that for any n greater than 1, if you apply to this measure our link, and I recall that this product is well defined, we can imagine that Mn is a row vector, and this is a matrix, and this is a multiplication of a row vector by a matrix on the right, and we get another row vector, which is the measure on the preceding level. So this relation must hold for any n greater than 1. So this is just the definition of a set theoretic projective limit. The theorem means that this set theoretic projective limit can be interpreted, can be identified with a space of measures on some space x infinity. And in this sense, this x infinity can be viewed as a limit, a projective limit, one can say, in the sense of category theory, it is the projective limit of this object in the category where the objects are measurable spaces and morphisms are Markov kernels. But it's not necessary to understand this claim. What we actually need, this claim. There is one-to-one correspondence between coherent families of measures, coherent families of measures, and probability measures on this space, which will be called the boundary. Why boundary? Because we can view this object, this chain, as a kind of Markov chain. Because these lambdas can be viewed as transition functions. Of course, this is not a usual Markov chain because time goes from in the reverse direction from infinity to 1, and spaces vary with time, but nevertheless one can say that with x infinity, one can say that is the entrance boundary of this a little bit unusual Markov, highly inhomogeneous Markov chain. So this is a non-trivial claim, and it can be proved in different ways. Here are some references. There are old papers by Dynkin, and Dynkin proves much more in much more general settings. Almost exactly the same claim is contained in the book of Winkler in Springer lecture notes. The volume is and the year 85, and there is also some adaptation of some proofs of this claim, which is contained in my paper in Journal of Functional Analysis. The volume and the year. I will use this abstract result. And here is some toy example illustrating this general theorem. The example is as follows. Say, take as x sub n the finite set consisting of n plus 1 points identified as 0, 1, and n. And we want to define the stochastic matrix. I will call these lambdas links. Links because they relate with various spaces in this chain. So to define this link, I have to define the entries of this matrix. And the definition is as follows. This is equal to n minus capital N minus small n divided by n if m is equal to n divided by the same quantity is m is equal to n minus 1 and 0 in all remaining cases. So these two quantities sum to 1, and it is automatically here that the passage from n to n is forbidden if n small n equals capital N, because there is no such point in this set. Okay. So the question is now, what is the boundary? And here is the answer. The answer becomes clear if we look at a picture. Here there's the level number 0 and the level number 1, the level number 2, and so on. And the transition probabilities are of such a kind. From this picture, one can guess that the boundary here is the unit, closed unit interval. And what means this theorem? Moreover, we have to define the links from the boundary to the corresponding space, which just gives us, what is the meaning of this link? It gives us the correspondence between the boundary measure and its component in the projective limit. So in this situation, this is given by the binomial distribution. As x is fixed, in the second variable, this is a binomial distribution. So this claim is a reformulation of Definetti theorem. And this is a useful exercise to understand this. And Definetti theorem, in turn, is equivalent to Hausdorff moment problem. I don't want to go into details. We can, if you don't know this, we can look at Feller's book. Or simply to Google. Certainly you will find Definetti and Hausdorff moment problem, and now it's very easy to find all the clues. So this is a simple example. So what is interesting here, we start from discrete spaces, even finite spaces, and we get, as a boundary, we get a continuous space. Now I'm in a position to describe the idea of our method. I would like to emphasize that this is not a very general method of constructing Markov processes. Not at all. It is a very special one. But the idea is, we will see in a moment, is very simple. It requires no advanced technique of probability theory, no Dirichlet forms, stochastic differential equation, nothing. Very general and simple arguments. Of course, they work, I emphasize again, only in some special situations. So this is, maybe one can say that our work is one more piece to the integrable probability, and nothing more. So, look again of our chain. So we have a chain of spaces. And assume that we are given for each space. So here we have links, some links, and we have a boundary. Maybe it's better to and we have links. Okay, and the diagrams are commutative. And assume that for each space we are given a semigroup, a Markov semigroup. Some Markov semigroup. And these semigroups are related to links, are compatible with links. What does this mean? This means that we have such an equation. for any t, real t, non-negative, and for any n greater or equal to 2. Then I claim that one can say that our links are intertwiners. Intertwiners for our semigroups. If you have such relations, then I claim that there exists a unique Markov semigroup on this space. And the argument is almost trivial. Indeed. How to define this semigroup? Fix T, fix, and fix some point at the boundary. And we want to define this object. And this should be a probability measure. So this should be a measure on x infinity. Some measure, and we know that this is nothing else than some coherent family. Some coherent family. So in order to define this object, it's enough to indicate what are these measures. And by definition, we say that m sub n, by definition, are as follows. We take P n P correct. No, I'm sorry. Sorry. Yes. There's no X. As follows. So we take the delta function and apply to it the link, and we get a measure on the level n and apply to it this operator. So this is the unique way that we can follow here. And then it is verified trivially using the intertwining relations that the measures which are defined by this way form a coherent family, so they satisfy the required relations. And so the definition is correct. They define some measures. And next we have to verify the Chapman-Kolmogorov equation. And again, it follows immediately from the very definitions. So this is a very formal way. What next? I recall that our Markov semigroups have been defined in terms of Markov generator. So how to verify this relation in practice? In practice, usually we do not dispose of explicit formulas for the Markov semigroup. But we have explicit formulas for the Markov generators. So the way to verify this relation in practice is to verify its infinitesimal variant. Namely, instead of this relation, one can try to prove this one. How to understand this? It's better to understand this as an operator relation in an appropriate space of functions. Namely, in this context, we have to read the both parts from right to left. So the underlying space is the space of functions on this space. So we apply, given a function f, we apply to it the links, which is essentially a matrix, and then we get a function on the space number n, and we apply to it the appropriate operator. In our case, this will be some difference operator. And the same for the right-hand side. First, we apply the difference operator, and next we apply this one which lifts to the next level. Of course, we have to prove that if the relation holds on the infinitesimal level, then it produces the required relation for the semigroup. But this is some technical result which holds under appropriate assumptions. We can, if you want, we can look in our paper and find there some necessary assumptions. And if we are able to verify this relation, that automatically, almost gratis, we get the boundary semigroup. Boundary semigroup. Let me give the example. I will continue with my toy example. What happens here? I have to specify the semigroup on each set. And again, I will specify this semigroup in terms of some difference operator. And the difference operator is as follows. It depends on two parameters, alpha and beta, which are supposed to be strictly positive real numbers. So I fix these parameters. And the definition is as follows. This is again a second order difference operator. We apply it to a function and evaluate at a point n, which is one of the possible values here. And the result is as follows. This is the forward derivative. And this is the backward derivative. Minus the backward derivative, actually. And one can verify directly, this is a simple exercise, that indeed we have these compatibility relations with the lambdas defined here and the difference operators defined here. Next, one can prove that this is indeed, this is very simple, because the space is a finite set, and you have a simple Markov chain with continuous time, with jumps like this. And once the jump rates are positive and the jump rates are these coefficients and they are positive, there is a Markov process, a continuous time Markov chain. And one can prove that using the result which allows us to go from this to this, we get a semigroup, and by the trivial general result, this produces us a semigroup on the boundary. And what is this semigroup on the boundary? Again, it is better to define it in terms of its generator. And the generator, in this special case, is a well-known differential operator, a second-order differential operator. The infinity. And one can prove that we have the following one more relation. That is, this link which relates the closed interval with the set of level n by means of a binomial distribution. It is an intertwiner between this difference operator and this differential operator. Of course, the result that we get here is the following, that there exists a Markov process with such a generator. Of course, this is a very well-known result because there is a well-developed theory of one-dimensional diffusion processes. And from the viewpoint of this theory, this is a trivial fact that such a Markov process exists. Of course. But this very special construction has the advantage that it can be extended to more complex situations when the boundary becomes some infinite dimensional space. Maybe I would like to add a few more details about how to understand the claim that it is a generator. In such a situation, formally we have to indicate precisely a suitable Banach space and the domain of a generator. In our situation, the Banach space is the space of continuous functions on the closed interval with the supremum norm. This is a Banach space, a real Banach space. And as a domain of this operator, I take the space of polynomials. The space of polynomials, which is dense here, of course. And the generator is well defined on this space. It is an invariant domain. And the truth, one can say more precisely that as an operator in the polynomial space, it is a pre-generator. And in order to get the true generator, you have to take its closure. Its closure in the sense of, as it is understood in functional analysis. And then we get the true generator. Why I take this space? Why I take this space? The reason is that this space is just the union, as n goes from 0 to infinity, of the images of the spaces of functions on our finite sets. Because this is a finite dimensional space of dimension n plus 1, and this object is a subspace on the boundary. And what is this subspace? This is just the linear span of the functions of the type I will write it in detail. This is span of functions of a form here capital N and small n are fixed, and we regard this as a function in X. So it is evident now that as capital N and small n vary, you get the whole space of polynomials. So this is a very formal construction which produces an operator here from operators from generators on finite levels. Now let's return to our situation. This is only an example. And now we have to construct something similar in the case of interest for us. Namely, now we take as X sub n our space omega, a point I recall is a sequence of integers. Now the next step we have to do is to construct the intertwiner. How to do this? And here we use some suggestions which come from representation theory. Consider the group, the unitary group of degree n, which is the space of unitary matrices n by n. And I recall a matrix is unitary if it satisfies this equation. This is a compactly group, and we are interested in its irreducible representations. I don't need substantial information about the structure of representations, how to construct them. The only thing that I would like to use is a parameterization of the irreducible representations. So in representation theory, the customary notation is group hat is the set of irreducible representations. For a compact group, this set is a discrete set. And it is known that this set is parameterized by the set of signatures. What is a signatures? A signature is an object which is close to a partition, but something different. So a signature of length n is an n-tuple of integers which are weakly decreasing. I would like to stress that I do not impose the restriction that all these integers are non-negative. They can be arbitrary. Given such an object, I can interpret it as an endpoint configuration on the lattice, because I define the corresponding L, because lambda and L is something related in phonetics. So this is, and by definition, this is defined as lambda sub I plus n minus I. The same relation already appeared in the talk of Alexei Borodin. So we can say that our set omega sub n is the set of parameters of a dual object for the unitary group. So given lambda, a signature, I will denote by pi lambda the irreducible representation indexed by lambda. And the following results hold. Take this representation and restrict it to this smaller subgroup. Here I suppose that this subgroup is embedded into the next subgroup in a natural way. This is a group of matrices of order n minus 1 by n minus 1, and to interpret such a matrix as a unitary matrix of a larger dimension, we simply add 1 here and 0 here. One can say that this is the subgroup in this group fixing the last coordinate basis vector. Okay. So given a representation, we can restrict it to this subgroup, and we get some reducible representation. And what is its decomposition? This is a non-trivial result, not very hard to prove, which is called Gelfand-Tsetlin branching rule. And the result is as follows. This is a multiplicity-free direct sum. Maybe it's better to add here the notation somewhere to emphasize that this representation corresponds to the group of degree n, and here we get something relating to another group, and the sum is over signature which interlace with lambda. Which means interlace. The interlacement relation means the following. Mu interlaces with lambda if the coordinate satisfies the relations, the betweenness relations. Now the construction goes as follows. Look at this equation and count the dimensions. Count the dimensions, and we get the dimension of this representation, that is the dimension of a space here, is the sum of the dimensions here. Let's denote it to simplify simply as sorry. So this quantity is the sum of these quantities. And now the definition of the link is evident. It is equal to the ratio of dimensions. If there is interlacing here and zero otherwise. Because the dimensions are strictly positive numbers, we get some probability distributions on the set of mu's which interlace with lambda. The next step is to evaluate explicitly this quantity. To do this, we need to know an explicit formula for the dimension, and such a formula exists. It is called the Hermann-Weyl dimension formula, and it looks as follows. Here I identify lambda and the corresponding L. So here I identify U. Say the identifications are as follows. U of n hat are irreducible representations of this group, which are the same as signatures lambda of length n, and which is the same as L's, which are in this set. Now the dimension formula looks as follows. It is the Vandermonde of the coordinates in L and divided by the product of factorials. And once such a formula is presented with this ansatz, one can prove by induction that indeed we have this equality. This is some exercise, not very easy maybe, but it can be proved because all is explicit here. There is a geometric interpretation of this, namely, say let n is equal to 4. We have lambda 1, lambda 2, lambda 3, lambda 4. And here we have mu 1, mu 2, mu 3, mu 1, mu 2, and some say kappa. And we have interlacing relations that mu interlace with lambdas and nu interlace with mu and kappa interlace with the nu's, which just means the betweenness conditions. This number should be in between of these ones and so on. So these the corresponding inequalities when lambda is fixed, describe some convex polytope, multidimensional, and once the lambdas are fixed, the other entries are just integer points of this polytope. And one can say this polytope is called the Gelfand-Zetlin polytope. So the dimension is the number of integral points in this polytope. Okay, so what next? What is the boundary? For I have defined the links in terms of the ratio of dimensions. And what is the boundary? I will describe it tomorrow. I would like only to say that the boundary also has a representation theoretic interpretation. A natural result is as follows. How to give a sense, how to find an interpretation of a boundary in terms of something. It is natural to take the infinite dimensional unitary group. There are many versions, many possible versions of unitary group, but for my purposes it's enough to define it simply as an inductive limit. Inductive limit, or this is just the same as taking the union of finite dimensional compact unitary group. So imagine that we have an infinite dimensional coordinate space, Hilbert space, and an element of this group is a unitary matrix, in general infinite, but it is essentially finite, meaning that outside some large corner, there are only ones on the main diagonals and zeros outside. Here there is something. Such matrices form a group, and this group is just the union of finite dimensional unitary group. Okay, so I defined the dual object as the set of irreducible representations. The natural idea would be to take again, irreducible representations of this group. But this does not go well because there are too many irreducible representations. This group is a kind of wild group, and describing all its irreducible representations is a so-called wild problem. So irreducible representations are in some sense bad objects. So what replaces irreducible representations? To understand this, it's better to switch to another language and replace irreducible representations by their characters. So a character, given a representation pi, its character is a function on the group which equals the trace of a corresponding operator. So given a group G, and pi is a representation of G in some vector space, to define the character, we take the operator corresponding to the group and take its trace. This is essentially the definition which goes back to Frobenius. Who defined the characters essentially in this way. And we are interested for compact groups, for finite groups, for compact groups, we are interested mainly in irreducible characters, which are defined as traces of irreducible representations. But this definition does not extend to the case of big groups like U infinity. It turns out, why? The reason is very simple. A typical representation, except some trivial cases, any representation of this group is infinite dimensional. And in particular, to define a trace means to define the trace of an identity operator which corresponds to the unity element of a group. And the trace is infinity. So the idea is to normalize this object. So let's consider normalized characters. Normalized character means that we take the character and divide it by the value at the unity element, which is the dimension. At least one can prove that this quantity is always of modulus at most 1. And there is a surprising result which allows us to characterize irreducible normalized characters in terms independent of any representations. Namely, consider the simplest case of a commutative group. If the group is commutative, then irreducible representations are one-dimensional. And they are characters in the sense of Pontryagin duality. So in the commutative case, a character is just a multiplicative function of the group, taking value in the unit circle. How to extend this definition to the case when G is non-commutative but still compact? So assume that it is not necessarily commutative by compact. What is if you adopt exactly the same definition that we get for typical non-commutative group, we get only trivial functions, say equal to 1. If a group coincides, if a group is simple, we can get only the constant function. The idea is as follows. First, we require that our future character to be a central function. Central, which also means a class function. Class function, which means that it is invariant under conjugation. It is constant on conjugacy classes. And next we modify this equation as follows. We require the following. Here I use the fact that if the group is compact, we have a natural uniform distribution on it. A unique measure, which is a probability measure, and is invariant under left or right shifts. It is called the Haar measure, the normalized Haar measure. As such an equation, in the case the group is commutative, reduces to the preceding equations, because this quantity in case of commutative group is simply G sub 2. But if you look at this on the left-hand side, we remark that it is a doubly central function. It is central relative to this argument and to this one. So this equality is natural one. Next, one can prove the following result. If G is a compact group, compact topological group, then functions satisfying these two properties, centrality and the so-called functional equation, functions satisfying these two properties, are just normalized irreducible characters. So this replaces the notion of a multiplicative function on a commutative group in the case of a compact and possibly non-commutative group. So in particular, this works well for the unitary group, which is a compact group. But now, what about the U infinity? It turns out that one can extend further this definition to the case of groups like U infinity, just by adding some limit procedure. Namely, in the case of U infinity, I will modify this equation as follows. Take here the limit as n goes to infinity. So I assume that chi is a function on U infinity, complex valued function, which is a class function, a central function, constant on conjugacy classes, and satisfy this limit form of functional equation, which makes sense. And again, one can prove that there are many characters in this sense, and by definition, the dual object is the space of such functions on U infinity, which satisfy the two requirements. One, centrality, and the limit modification of a functional equation. So this is only the definition, a formal definition. And now the theorem which will be made more concrete tomorrow, says the following. Return to our situation. I recall that we have the chain of spaces which are duals to the unitary groups. And the theorem says that the boundary is exactly the dual space to U infinity in this sense, the space of quasi-multiplicative functions, one can say, on the unitary group. Of course, this is some abstract result which says nothing about the size of the space. Maybe it's empty, or it's not empty, but of course it includes the constant function, but at this moment we know nothing more about the size of the space. It will be shown, I will be explaining this, that the space is indeed very large, it is infinite dimensional, but still it's very good, it's not pathological, it is a locally compact space. And what's next? Next I can formulate the result. The result is as follows. You have again these chains, and we have a boundary, and you have semigroups which are constructed in terms of some second order difference operator. First of all, the result is that the semigroups are compatible with the links. So by the general result, this produces a semigroup on the boundary. And what can be said? How to verify it? Again, we have to verify compatibility of difference operators. So look, all is explicit now. We have explicit formulas for the links, and you have explicit formulas for the difference operators. And these difference operators define as the jump rates on this set. So in principle, it can be verified directly. The relation that we need is, I recall it, But it seems to be difficult to verify it directly. And indeed, in our paper, we use some machinery of symmetric functions, some combinatorics of symmetric functions, to verify this relation. And next, we prove that indeed this gives us compatibility on the level of semigroups. This also requires some work. And finally, we arrive to the boundary semigroup, for which we prove that it defines correctly a Markov process. In our situation, I would like to stop here and to say a few words about some technical problems which arise here. More precisely, what we get. The situation is more or less the same with some complications as compared with the case of our toy example. Namely, in the case of our toy example, we worked with the space of all functions. But here we have an infinite set, and there are two possibilities. We can take the space of all functions, of all bounded functions, bounded functions. But it's better to take the subspace of functions vanishing on infinity, which means functions vanishing at infinity. Vanishing at infinity just means that outside a large finite set, the value of our functions are very small. This is a closed subspace in this Banach space, and what we prove actually is the following. We prove that our semigroup is a failure semigroup, which means that these operators are well defined, on this space. This is a separable Banach space, and this space is not. Next, we prove that our generator, and this space contains the algebraic subspace of finitely supported functions. Finitely supported functions. And we prove that this subspace is a core for a future generator. What means the core? Of course, our difference operator is well defined on this space and on this one. But we prove that if you view our difference operator as an operator inside this space, its closure gives us the true generator. So this, one can say that this relatively small subspace is an essential domain for our future generator. Usually in such questions, it's difficult to describe the domain of a generator of a Banach space semigroup exactly. but it suffices to describe its restriction to an appropriate essential domain called the core. So we prove that this subspace is a core. And next we will prove that our future generator of the boundary semigroup is well defined on this space. This space will be a core, an essential domain for the generator of the boundary semigroup. And this space can be viewed as an analog of a space of polynomials. I did not define what is my omega. I will define it later. But I would like only to say that we can produce some analog of a space of polynomials. And on this space of polynomials, we are able to define our generator. And in appropriate coordinates, we will prove that this generator is a second-order differential operator. This is in contrast with the situation which arises in the case of a Dyson model. Because as far as I know, in all papers, the authors did not manage to write down precisely the generator. But finally, I have a few minutes. I would like to try to explain in what sense our picture is dual to the Dyson picture. I would like to stress that this duality is informal. It's not formalized in any strict sense. But what this means? The source of a Dyson model is the Brownian motion on the unitary group. Namely, take the unitary group. It is a compact manifold, and it also carries a natural Riemannian structure, which is invariant with respect to left and right shifts. And there is a Laplace-Beltrami operator, Laplace-Beltrami operator, second-order operator, which is a two-sided invariant, and it is the generator of a Brownian motion. The Brownian motion on the unitary group. This Brownian motion, by the very construction, it is invariant with respect to left and right shifts. In particular, it is invariant with respect to conjugation by unitary matrices. And what are the conjugacy classes in this set? The conjugacy classes are parameterized by the eigenvalues. So we have a natural projection on the conjugacy classes, which are the same with eigenvalues, in my notation, and tuples on the unit circle. And it turns out that the Laplace-Beltrami operator admits separation of variables with respect to this projection. So we can introduce some kind of angular coordinates which are responsible for conjugation by unitary matrices. And in this system of coordinates, eigenvalues can be viewed as radial coordinates. And there is separation of variables, And we get a differential operator on this space. And this is exactly the Dyson operator, which was at the very beginning of my story. And due to the separation of variables, we get a kind of Brownian motion, a kind of diffusion process on the space of endpoint configurations. So one can reformulate it as follows. The Dyson model is a diffusion process on conjugacy classes, while our model on the finite level n is a Markov process on the dual object. Dual here means in sense of duality between conjugacy classes and irreducible representations or irreducible characters. In the simplest case, say of a case of the circle group, which is both compact and commutative, the dual group is the lattice. But in the case of a compact group, the dual object is the set of irreducible representations, F. And this is some fundamental fact of a theory of representations, say, of finite groups, that the conjugacy classes and the irreducible characters have the same cardinality. But they are not, despite, except, maybe it's better, except some special situation, they should not be viewed as sets which are isomorphic. They should be viewed as sets in duality. This is the sense that I give to duality between the Dyson model and our model. But what is, I would like to emphasize again and again, what is indeed surprising here is that the Dyson model seems to be very fundamental and very simple in formulation. Our model looks much more sophisticated. It includes 4 parameters and some jump rates, which are defined in a way which require some motivation and so on. But surprising is the fact that in our situation we can go further in our analysis, due maybe to some tools which are provided by representation theory. Perhaps there exists some future theory which unifies both this case and this case, the level group case and the dual case, but at the present time it is unknown. So tomorrow I will describe in detail what is the boundary and what is the generator of the semigroup. Thank you.